May 23, 2023. Differential analysis. It's been the topic of discussion. And the last time there was getting into Legendre and the Legendre equation and the idea that for 1 minus x squared for p, y double prime, and that for negative 2x for q, y prime, plus n minus 1 y equals 0, that filling out this general form for a second order equation, py double prime q y prime r y equals 0. That for the Legendre equation, then there's the Legendre polynomials that were described and their features in the development for that for p sub n, that they're orthogonal, these polynomials, that so for n not equals to m, that the integral of pn times pn dx equals 0. And then there's this and accords some sort of weight function, so that in the orthogonality, that when taken together, that their integral is 0, because basically one's above and one's below the axis, so they sum up to 0, or rather that their product is as to like so, say. That there's then that there's a weight function that makes it so normalized, so that the integral of one or the other is 1, as it were. And so, and then I found out that that's just a part of this, what are called the classical orthogonal polynomials. And there's a bunch of them. There's like these Gegenbauers or something like that, and the Legendre, and up above that Jacobi or sorts. And then there's some more of them. And then that even those are all sort of parameterized as according to what's called Askey, A-S-K-E-Y, Andrews and Askey of the late 20th century. They made a categorization of all these common orthogonal polynomials, and so there's a ton of different ones. And so for all these various kinds of systems, it arrives at there's various parameters in terms of the alpha, beta, and gamma, for example, where alpha, beta, and gamma equals 0 or 1, or that there are these various parameterizations of these forms of these polynomials that end up making them very schematic in this sense, and the ability to consider those. It's always nice to find somewhere in mathematics like this whole hierarchical organization of things, whether it's Plato's solids or the rules for a polygon or this or that, that as it goes out, that this richer higher order form has a name and a place in a catalog of these things. Kind of like if you look at, Stegen and Abramowitz, or the Handbook of Mathematical Functions, or the Digital Library of Mathematical Functions, and all these special functions that exist, or the table of integral series and products and these kinds of things, or here that these polynomials that are in these families of these other even more so, all these kinds of orthogonal polynomials. And then that they're part of basically then in continuous functions, all these orthogonal functions and the continuous functions like sine and cosine. And the great facility of those with respect to the transforms, and in the differential analysis, in what regions for what equations, what transforms are in effect, that it then makes it possible to treat these systems of equations analytically, or according to manipulating the equations into other ones and making derivations according to the quantities and the conditions and constraints and this kinds of thing. That the utility of that is to be very highly regarded. And then as well, what's nice is to get figured out that what are some of these fundamental theorems is about the just the properties of their products in the terms, that they're orthogonal functions, that their product is 0, or the integral of their product is 0, or something like that. Makes it so that then they can be sort of, as it were, treated as the additive identity 0, or treated like the multiplicative annihilator 0. And as has been discussed here in terms of the methods and analysis about the differences in quantities between the additive identity 0 and the multiplicative annihilator 0, And when arithmetic is defined just in terms of addition and division, so where 0 is division is or isn't closed to 0, whether it is to infinity and just results the additive annihilator is 0, and whether addition is closed to increment and contains the outside term infinity, about 0, 1, and infinity, that it very much pleased me to notice that compared to the state of affairs over the 1600s, 1700s, 1800s, and 1900s, where these families, these polynomials were developed, that now there's catalogs of them and how it can be possible to organize, thusly, forms in them. And then that besides that the operator calculus helps make that an abstract thing, and about the ability to theorize the existence of orthogonal functions generally, and to look for various kinds of orthogonal functions in the standard and non-standard. So for these classical orthogonal polynomials, the idea is that when there's true standard character of non-standard functions, to figure out how to make these non-standard functions have what would be an extension of this notions of the orthogonal functions, for example, into higher dimensions, or in terms of singularities. Then for something like the differential geometry, which really has a lot going on, like in terms of the hypergeometric, which is after the power series, then or the geometric series, then the hypergeometric series, and then how that is in the differential equations, and how that is in the probabilistic, because these systems that affect and reflect relations in the concrete show up in a lot of the different fields and subfields for the discrete and the continuous. And then particularly for the non-standard is what happens in the middle between the discrete and continuous. What's that middle of nowhere for the induction either way that makes that 1/2 between 0 and 1, that makes that 1/2 of 0 to infinity, or with respect here to usually just that 0, 1, and infinity, or for example, are the regular singular points of this hypergeometric differential equation. So that amused me quite a bit, and in terms of a lot was extracted just from the classical text that doesn't have many diagrams, few if at all really, and is mostly just in prose, and then also from it, reading the treatises of the fin de siècle, the 1900 era, because it was before algebraic geometry and point set topology were applied to the objects of the analysis and made as the foundations. So as a different mindset, a different worldview, and the objects though are the same. They're the same objects. And so then when it gets to how it's necessary to treat these same objects of 0, 1, and infinity from these dynamical systems, it's mathematics, in terms of when and where and whether that either becomes arbitrarily contrived or contradictory in a point set topology, or what that means for topology basically ends up being the question. And that is where there's usually an opinion, an analysis that there's a topology, and it's the open topology, and this is how it's made, that all the developments kind of are derived as from it. There are others, and so what happens in between the discrete and continuous, in the discretization of the continuous, or the emergent of the discrete in the continuum limit, it has to do with these topologies and whether they're linear or singular, or linear or nonlinear, and when they're standard in the sense of that the limit is the expected value is extrapolated, interpolated, or they're non-standard and anti-inductive, that they end up having different values for what's between them or something like that. So these are the kinds of things that amuse me, because that's not very well filled out yet in mathematics, but it is really a thing. And so then all these contrivances and stuff that build to them make it so that a lot of the developments end up being very extended and carefully so. And then in terms of particular touchstones of application, like the Jordan measure, which is discussed when reading up on the path integral, and the Dirichlet's problem. This has been about reading about for the potential theory, that a lot of it is framed as of the harmonic theory of harmonic functions. But really, it's just about supermodels of classical physics that have infinite flow of what would be the contents in the field, or the gradients in the field. Okay. So that adds up for all the potential fields, that those forces resulting all end up being defined in terms of the contents of the fields in this and that, in physics, say, where physics is the basic model application for mathematics and applied, vis-a-vis, economics, or the mathematical sciences, or any aspect of the sciences that is the mathematical part, the interpretation of the model, so sign and so fitting. It's been discussed, the aptness of metaphor, or the failure thereof, and these kinds of things. That, when it comes to the ideas of how to solve for things like the unified field theory, like as Einstein had put it when reading Einstein and out of his later years and all this kind of stuff, that he, as he puts it, he says it's a total field theory and it's differential. And I've left relativity so defined so that it fits in that regardless, no matter what. And so you just have to deal with my mass energy equivalence in the rotational, and that special relativity is local and makes so an effect for that light speed is a constant, and there's a vanishing cosmological constant that, as you see fit, lives in your gravitational field equations. And then for the Riemannian metric and the Euclidean metric as arbitrarily two different things, and arbitrarily where they live is basically the bounds about the object and this and that, or when the inverse cube or inverse square or inverse have these various regimes in gravity and long distances, like the modified Newtonian dynamics theory of today seems to predict with arbitrarily high precision for the sky survey of all the things. That is left so that way, that then, as he puts it, and it's a differential theory about this continuous space manifold and the contents in it, and of the time, and about how the time dilation in that theory is as a result of the space contraction of movement. And then that the movement of objects, as they're being continuous as well, on this absolutely continuous overall manifold, it ends up making for a theory of space contraction, and like for the fall gravity we can point to Fadio and Lesage, and for the space contraction we can point to Fitzgerald and as before Lorentz and about Lorentz and these kinds of things. And so then those again reflect that, going back to the theory of harmonic functions and how they solve the Laplacians, because any harmonic function is just that the Laplacian of it is zero. And so it makes for, as a bound about either side of the second derivative, or you'd call it for time, it'd be acceleration or maybe deceleration, depending. That then we talked about, there was this discussion of acceleration and the integration that arrives at velocity, and also the stopping distance, and then what that means in terms of those being basically alternative notions, that there are differences between accelerating away and coming to rest in terms of bodies in their place and this kind of thing. So in that sense, there's a lot going on, even with regards to classical motion and this and that. That backing into the usual milieu of the differential systems as of the plane curves and level lines for usual things, and then the various applications of differential systems, which reflect the rotational, which reflect the growing, and which reflect the all such manners of systems parameterized by time, where the rate of a thing affects the rate of a thing. That there's feedback in a sense, or when it reaches in the middle, like this x times 1 minus x for x between 0 and 1, that for 0.5 and 0.5, that's 0.25, but pretty much otherwise it's less than that. And about root mean square, that gets into a lot of different things. And so it's pretty amusing. And the idea is to keep it pretty amusing, to have a top-level catalog of all of differential analysis, to have it clear and firm what are the similarities of what are the differences between the fin de siècle analysis that it is and the definitions, and the Y2K analysis and definitions, what they are. Because they're one mathematics and they treat the same objects. And the definitions need to be made clear as to why that's so in this kind of catalog. Then the ways to figure out how to approach these other notions of the forms and this and that can go a long way to helping to disambiguate what's otherwise a larger and largish field, and to keep it so that the subfields don't end up being mutually contradictory or unable to agree with each other, or fraught with ambiguity, risk, and the according to Murphy, the certainty of their getting it wrong. That these are some of the kinds of things that can really help, or at least from my perspective, even just these readings have helped me feel like I have a better grasp, grip, and understanding of differential analysis. That then we can get to some of these simple things and then figure out how to deal with some of these, what are these non-standard toys, or these toys, and or these fundamental elementary declarations and definitions that make up so that they are widely apt and central in other models, and then that they result the ability to break down and refine some of these otherwise whole systems into those which then make for otherwise solutions for methods of symmetries. For the ideas then that is back to these symmetries and these sheaves for topology's sake. So these geometric symmetries fundamentally, and these topologies sheaves where the topoi are the spaces and the points and elements in them are the discrete elements in these continuous spaces fundamentally, for points, lines, surfaces, and so on from geometry and points and spaces, for points, lines, surfaces, and so on in topology and its spaces, for topology defines the neighborhoods of these things, and basically the dynamics of what would happen would be dynamics in topology when topology changes. And then for these submersions, that the submersions are the and immersions is our submersions and immersions are complements. That the submersions either make for closed forms in the analytic because it's able to frame certain problems as solvable in a closed form, but then for other ones it just provides numerical methods with infinite series, of which computing the first initial segments can provide a large part of the value, then about their error terms, and they're bounding their error terms, and why those are a compromise or a trade-off of tractability for understanding. Because if those systems really had a closed form solution, it would be exact, and when I say exact, I mean perfect, compared to when it's just an analytical method then affording a numerical method that is tractable and will give good values, but not perfect values. And so that there is truly a difference in that. And then going back to then some of these notions of the motions of the plane curves, about the plane curves and integral equations, and about how differential equations end up getting solved back by geometry again. So then there's these notions of the symmetries and for geometry, and in algebra as about the elements of the geometry, because the algebraic geometry is either algebras or geometries, and they're two different things. And because any geometry models all algebras, basically objects of geometry and elements and forms and constructions in geometry. Then there's the topologies notions. What is nearness? What is density? What is neighborhood? What are critical points? What are the degenerate intervals that make points? what is the deconstructive accounts of the pseudo and the quasi. It's really, it's a thing about how between the continuous and the pointwise, inductively, either way, neither one arrives. You can put points together until infinity, but it's not a continuum unless it's kind of as so broken down, and vice versa. Putting them together makes for the way to establish that there is a meeting in the middle, that there is a square at all. And it's nice and simple about that then, because it is one universe of the mathematical objects, which it is. And it also helps a lot to explain things like, well, what's a point-like object in physics when we have, what's a surface-like object in physics? You know, how can there be both? How can there be either? There are both. There are either. And then according to induction, then it says, and it's as results according to this deductive results, that explains why and what there are these effects and behaviors for the descriptive and the differential, the dynamics in the middle. So I'm glad I picked when I started reading about the differential, this idea of descriptive differential dynamics, because it reflects what it's all about. And the descriptive, of course, is from descriptive set theory. It's like, well, what is descriptive set theory? Well, it's a book, and I think it was by Moshe Vakis or so, and excuse me if I got that wrong, but he at some point in time, there was this wonderful book, and it's called Descriptive Set Theory. And basically, after following axiomatic set theory, or Zermelo-Fraenkel set theory, where there's axioms of usual expansion and comprehension, like sets are sets, subsets of sets are sets, subunions of sets are sets, and these elements and so on. Let me define an empty set. Well, that's kind of non-standard, but that's a restriction of comprehension. There's only one, or that each type has their own. There are many ways to define that. So it's the other axioms being expansion and comprehension, then there's define in zero, and then in an infinity. And this infinity is also well-founded, and which means that when Russell gave Frege a paradox to prevent Frege's theory from coming up as the foundations, then when Zermelo-Fraenkel came up and you could apply that same paradox to what would otherwise be a set that's infinitely big, then they just made an axiom that said it's not. It's not the set of all sets that don't contain themselves, thus it does. Russell's paradox. And then there's the axiom of well-foundedness or regularity, which basically says, and no other set has a relation that relates to itself either. Now, of course, does that mean the fundamental axiomatic set theory? That's fine. It's fundamental axiomatic regular set theory, and it's got pretty much the minimal number of restrictions necessary to make it a one-sided case for infinite induction. And then some people attach to that, they hang their hat on that being infinite, is fair in many cases, but in many it's not, because it builds up for counting, and because Descartes already provided all the space for the functions, and so it already exists, because the power set theorem makes the sets exist, even if geometrically such a thing could not exist. And so it's axiomized to exist, though, and it does in mathematics, and so that's great. So it makes a case for infinite induction and transfinite induction. It's fine. But what it does, though, is that the mathematics also has theories that has the infinite that is extraordinary. That it's more like the numbers and ordering and ordinals instead of sets and counting and relation and functions. It just is. They're just different. It's the way it is. So anyways, after axiomatic set theory then became the milieu for a lot of the foundations of mathematics, because you can write so many things in it neatly and naively a lot of the time. And the set builder notation is very familiar, and it admits union and intersection after Venn and Boole and De Morgan and all these kinds of things that make for the geometric, that the intersection and disjoint and union add up. That's great. Sets have very natural arithmetics and algebras in terms of operators on them, which are set-like for the regular, ordinary, well-founded sets. So anyways, the descriptive in the set theory then is an effort and a treatise to basically build everything in terms of sets and objects as being of types of sets, and then for those kinds of objects, those modeling various mathematical objects from all these different fields, then the idea is that the functions that exist between them make for the operator calculus that, according to the algebras and stuff, you can make all the proofs up above symbolically that then say that everything and each thing is kind of set. They all live in the same set theoretic universe. Now, that's not to say that a set theoretic universe exists, because, well, it doesn't in ZFC. You need extra axioms, or rather less. The idea being you start with an axiomless system. You arrive at that, you arrive at all the expansion of comprehension, then you arrive at the restriction of comprehension as basically preventing inconsistent multiplicities, but you can still have the extraordinary infinities because they're real. And these kinds of things about what it takes to get the theory past paradox. There's no paradox in the universe of mathematical objects. They're mathematical. They reflect truth and relation. It's very simple. So, descriptive set theory became the milieu of saying we can describe any kind of object in a theorem, and structurally for constructivism any kind of mathematical object as having a model and sets that are working milieu as model theory. And some might say, well, it's proof theory, but one way or the other they're the same, because one way or the other they're going to have elementary things, and it's either one theory or not. I mean, you can have 5 billion different proofs and 5 billion different theories, and then you can pick and choose them together naively if you want. And that's a fair, pragmatic, heuristic approach, and I think it's most people, it's in most things. But when it comes to foundations and one theory, it does not suffice. It's modeled inside the one theory as that, and not vice versa. So model theory wins, in a sense. So the descriptive part is like so of this descriptive differential dynamics. And then the differential part is because it's about the derivative and the differential equations. It's named after Leibniz, the differential, I suppose. Newton had his fluents and fluxions, where the fluents are the wholes and the fluxions are the parts, you know, and or the infinitesimals. And Leibniz said his differential, and and both of them framed it in terms of ratios and quantities. And there came this one fellow who's a critic of the whole thing. He said there cannot be infinitesimals. There would be ghosts of departed quantities. But if you ever actually read Berkeley's article about the infinitesimals, it can be read because it mostly examines them as to why they are in effect. But then at the end he says, and now you can read this as a veiled sort of criticism, because I can't actually write it out this one way, because even though the Spanish and Roman Inquisitions are over, it would still not serve me well, and ... But it's important to read the original sources sometimes to get a little bit better idea of the context, than that it was just rejection, and that people who had picked that up by its sleeve, or it's kind of like a foolish consistency, the hobgoblin of little minds, or something like that, which goes on to say, but you know, be dogged, in your results. It's context. Whereas in a universal theory, the theory is its own context, and it just adds up. It's not paradoxical for it to be dually so. It's dually so. So anyways, the differential is like to so, then it's about the continuous in analysis, and the dynamics in the continuous in analysis, about the infinitely divisible, harkening back to Zeno Elia or so, and there's several Zenos, I guess. There's like Elia and Megar or something, I forget. But anyways, the paradoxes are about the infinitely divisible, and they can be read one of two ways. They can be read one of ways like it's impossible to have things that are infinitely divisible, or it's impossible for them to add up, or they do. And it's a matter of deduction where and how they do. It's a matter for the dialectic, and it's so they do. And so that really has to be framed very centrally in the theory from the get-go, to make it so that the dually self-infraconsistent objects of the theory can start with one object at all, whether it's a void or a universe, and arrive at anything else. Of course, this is just old hat, old hat. And what that means is that it's an ongoing metaphysical debate and even dispute since antiquity. And over time, it starts most books in the world to keep people's attention. Why is there something rather than nothing, as it were? So anyways, the differential then reflects this whole central notion of motion and change in motion in analysis. And then particularly that besides the usual notions of the functions that are integrable or indifferentiable that aren't yet differential themselves, they're not defined in terms of their own rates of change, or they don't have the feedback so associated with them, then it's to be found that many and most sorts of natural things have some level of hysteresis or feedback that make for that they regulate themselves, these systems. And so that's fundamentally differential. So then these notions of the physics of the attenuation after dissipation is kind of this one way. It goes out it goes. And then this restitution and oscillation is basically this idea of that's regular, and that also that's regular, the restitution and oscillation, that something regulates itself vis-a-vis that it's regulated in terms of, like, in the outer point in space, heat goes out and everything goes to a cool equilibrium, compared to an object in motion stays in motion, like a top on a table while it's still spinning, and still finally something will let it down. Or something that the Earth spins around, in a sense. It's just an example of that. Besides that, time keeps on slipping into the future. It goes around and around. So these kinds of approaches help to make it so why this axiomless natural deduction is a real big thing for foundations. Right? So in descriptive differential dynamics, then we're getting back to the elements. We're getting back to the elements of the geometry and the elements of the axiomatic set theory, and we're getting back to the models of the descriptive set theory and the models of the analysis, models of the number theory, and the notions of functions. So the functions end up being a primary theory of sorts in themselves. They relate things from one to another. And given that there's any kind of interpretation of one thing or another according to this function, whether this function is to represent intentionality or extensionality, or it represents a transition governed or regulated by some other effect or a scale or a coefficient or any kind of formula or function you want, then there's like the whole world of functions, the space of those, in terms of then it's sometimes some functions are quite direct and they don't really admit anything else. They live in all one topology. They, according to one time, they're linear. They go to the other side. In terms of then all the space of the functions they could be multivalent. They could have anything you can ascribe to any number of given spaces, as long as you have the domain and range in a Cartesian product, or arrayed against each other, with one for each and the other, and then you can have any kind of value in those that reflects in any of the other spaces, any kind of this projection of the image, the image they call it, of a function, for a domain and a codomain, or a domain and range, or the image and the co-image, or the domain and image. You'll find the word image used a lot in terms of the theory of functions. And you'll find domain used first and range used second for the left-hand side and right-hand side of most functions. Or domain and codomain. Or, again, image and co-image and this kind of stuff. And so the function theory has a lot going on, and it's kind of as primary as set theory or number theory and this and that, because it affects the relations. And when you think of that, sometimes these subfields model each other, like point set topology and geometry. And then, well, what are functions in geometry? Well, there are sorts of constructions. I mean, they live in geometry in a sense. People often have the geometry or the world measure is, geometry, the world measure, ends up being the fallback field for everything. But we have all of axiomatic set theory and all of descriptive set theory and a whole universe in transfinite, and as well we have function theory and all the Cartesian, including Emile de Bois-Reymond's long line for the infinitar calcul, and even non-Cartesian functions like this line drawing, this geometric again for revitalization, and for Hausdorff's approach to the Banach-Tarski paradox and the doubling spaces for topology, vis-a-vis the modern algebraic approaches, say, which have different results. There's Cantor space, and it's uncountable. There's square Cantor space, and it is countable. One is about, in one exists all Cartesian functions, and the other there is not. There is only one non-Cartesian function. See? So these are the kinds of things that get into the differential analysis then for the dynamics. So what's the dynamics and how do they go on? I guess when a lot of people think about the differential function, it's about the exponential function. Why the exponential function? Because its derivative is, again, e to the x. Carrying down constants and multiplying it. So the derivative of, and again, any mistakes are my own, and I'll correct them if I find myself wrong. E to the 2x, you take its derivative, it's 2e to the 2x. E to the million x, you take its derivative, it's a million e to the million x. That's the slope at that line. If you plug in the number for x, that will compute it for you. For f of x is the value, and f prime of x in Newton's notation, or df dx in Leibniz's notation, is that. So the exponential shows up a lot in all the kinds of ideas of the rates problems. And it becomes very familiar in this. And there's not many other functions that are their own derivative. There's zero. And it's well known that for many systems of differential equations, zero is the trivial solution. It shows up a lot, shows up. Then there's and that's kind of for the system of the approach to the differential equations instead of the plane curves. And when you start with the plane curves and find their integral equations again, that for me was a lot that I learned from this book by Ersey or Emery, or who is this? ELNC, ELNC that we've been reading. DSC, lectures in, let's see, what does it say? Lecturer in Technical Mathematics in the University of Edinburgh, formerly Professor of Pure Mathematics in the Egyptian University. Ooh. So this is from Edinburgh, from Inner Science Publishers. So before Wiley became Wiley Inner Science, this is Inner Science. And so the plane curves and the integral equations offer a lot of different methods that make for a bunch of different things going on about when is the differential the same as the function, or when is the integral the same as the function. So I really found it remarkable to kind of take a look at something like this sweep function. Okay, now this whole idea of the square Cantor space, this is only available as far as I know from me. I've invented this, I've contrived this, I've discovered this, and give it a description. And so anyways, so this function is taking 0 and 1 and splitting it up into infinitesimals. It's just it's constant monotone, strictly increasing from the integers, the positive or non-negative integers, 0 to 0, and 1 to 1 iota, and 2 to 2 iota, and 3 to 3 iota, ... The infinity iotas is equal to some 1. So it's simple. And it's simple, primitive, fundamental, essential, and it's having been put through the ringer of applying it to all otherwise the proofs of countability. that shows it's sort of unique and shows it's a sort of counterexample and shows why there exists a world of non-Cartesian functions, and this is one of them. And it really builds the first way to have a measure theory about 1.0 about this line drawing that's so simple, central, fundamental, and perfect, and part of mathematics. So goes in the theory. So anyways, it's its own antiderivative. And is it even a continuous function? In a sense, but really it's the discrete to continuous function. You know? But in arbitrarily small change in the domain, which is only defined on the integers, is an arbitrarily small change in the range. So, and it's ordered, so that would make it a continuous function. There, you can't extend the range. It would break its definition. You can't extend the domain. It would break its definition. It's kind of so. So anyways, is it a discrete function, meaning its domain is discrete, or is it a continuous function? It's in the middle. That's what makes it kind of special. It's the function in the middle. It's Aristotle's continuum. It's a model for Zeno of after parts the analytical character thereof. But it's also kind of funny because besides being this in the middle, and it would look like a triangle, so whatever, area 1/2, and then you split that up into infinitely many bits. It's still just a constant ramp from 0 to 1, but its area actually, when you finally get to where it's infinite, its area equals 1. So it's a non-standard function of particular interesting analytical value. So it's a way to look at a singularity as of for the range 0 and 1, you can take its inverse in a sense, and so then those relate to the integers, and as well that it's length 1 and this kind of thing. So the idea is that it's almost what looks like the trivial function, or like 0. You know. While what the idea here is for this differential dynamics has been that's been brought in a long time as what's called the spiral space flowing curve and everything that goes into making something like that. But then when there's this identity dimension, the idea about the identity dimension is what I want to figure out about it is that these singular points at 0 and 1 and infinity of it are to contain any number of ways that this kind of spiral, like one of Descartes' vortices, or the spiral, or an arbitrary impulse. Again, speaking back to Descartes. Descartes got a lot of ideas about the standard and non-standard in mathematics, and or what there were of those at the time were kind of attached to Descartes' ideas. Because as a school of a man, that doesn't reflect all the different people who are involved in kind of forming this kinds of opinions and the canon and stuff like that. So then it just becomes associated with Descartes and Descartes' vortices and Descartes' notions of the impulse and this kind of stuff. Or as I call him, Uncle Rennie, Uncle Rennie. So anyways, the idea is then about these singular points is that they have any notions of this chaos theory, but dynamical methods. Chaos theory is kind of outmoded. We just call it dynamical modeling. But what it reflects is that there is, given arbitrary inputs to a reasonably easily contrived differential system, it could have arbitrarily large output differences. It's not continuous in the sense of inputs versus outputs about the configuration space and the change of things. That each intermediate step, so defined by how it's parameterized, as usually by time, is still continuous. That's how it is. To avoid discontinuities of various forms, that those end up just becoming defining complexity and shape and flow and this kind of thing. or about the emergent, or about the decomposition. These are these kinds of things. The idea is to try to figure out how to have, if there's more than one function that's its own antiderivative, then any of the kind of tools that get applied to the operator calculus about the exponential, because it's its own antiderivative, and so that under the exponential it becomes free to take higher and lower orders of it while dropping it out as a constant of a sort, or multiplying in its constant, or dot dot dot. Same idea is to be applied to this other function that also happens to be its own antiderivative. And so the idea then is to take, when there's the taking of the derivative of this function with respect to its antiderivative of basically the inverse of this function, about 0, 1, relating to these numbers about it, the integers at uniform random as they were. That's kind of the thing. And this speaks to another one of this central aspects of this continuity function, or sweep as it were, natural unit equivalency function, is that besides being its own antiderivative and that its area equals 1, that thus its length is 1, that thus it's both its own antiderivative and it's a probability distribution. And the domain that it defines as having a probability distribution is the integers at uniform random. That it basically arbitrarily picks at random from the infinitely many integers, including the infinitely large. So like a billion is likely as a billion billion, is likely as a billion billion billion, is likely as a gazillion to be this next sample. There is no mean, it would be half infinity. And so that's basically the same thing as trying to define a uniform distribution over 0, 1. We'll take a sample because 0, 1 has a mean, it's 1/2. And what can you say about what sample you get out of it? It's like, well, how precise can you get? It's a limit, it's a function of that. But at the same time, the uniform probability distribution in probability theory is usually only defined on, as it's normalized and standardized, to 0, 1. And that any particular interval is as likely as any particular same length interval in it as being the result of a sample. That otherwise all the usual results about probability theory apply to it as a distribution. And it looks like a square in a sense, you know? So here, the fact that it's also a non-standard distribution, then that gets into that there are also other ways to compose the equivalency function with itself, like the reverse equivalency function is just like 1 minus it. So if f of 0 is 0 and f of infinity is 1, then g of 0 is 1 and g of infinity is 0, the reverse equivalency function. So you take that over 2, and that's another function that's different than this function, but it's another probability distribution of the integers at uniform random. And this is another boggling thing about probability theory, because in probability theory it's shown that there's only one there's only one distribution function for each distribution. There's a PDF there's only one PDF for each distribution. There's only one CDF for that same distribution. There's only one MGF, moment generating function, for that same distribution. The uniqueness. So here's like, you mean it's not unique in probability theory for this non-standard distribution to have a unique distribution? It's not. It's remarkable. And so this is similar with the CDF and stuff like that. So it's pretty remarkable then to try and figure out how, for the standard, now taking the fin de siècle of differential analysis, then the Y2K of the modern linear curriculum and its schools and its fields and its subfields, And then to get into stuff like this, contributions to nonlinear partial differential equations, that they get into a lot of different things here about realms of subfields that also have large things going on, and also they have a lot going on with the non-standard, like the martingale, or otherwise not the non-standard. There's been some reading from this in the earlier discussion about exact regularization or critical point approximation, variational approach to the existence of skyrmions, optimal multiplicity, and local bifurcation theory. Well, that might be pretty linear and standard, but these other ones are about, for example, finite dimensional attracting invariant manifolds for damped semilinear wave equations. Semilinear means degenerate, pseudo, quasi. These are the things which get into the nonlinear parts of partial differentiations, as the title suggests. Contributions to nonlinear partial differential equations. So, these are the kinds of things where I'm looking to get, instead of higher in mathematics, lower in mathematics. So for something like the application de la theorie des operators subpotentials au control stochastique, that they start to make sense in terms of this discretization and continuity more generally, because mathematics really needs at least 3 definitions of continuity if it's going to have a flexible enough vocabulary that it's able to phrase these higher level results in much less vocabulary. Continuation and comparison methods for some nonlinear elliptic systems. Some remarks on semilinear wave equations in Rn. Recent results on the quasi-variational inequality of the impulsive control. An L1 method to prove global existence in some reaction diffusion systems. Existence in asymptotic behavior. Convexity properties of the solutions of nonlinear heat equations. Some open computational problems in quantum lattice theory. The quantum lattice has been around a lot longer than quantum computer. Singularities of some degenerate elliptic equations. Yeah. So these are the kinds of things that get into then figuring out how to take then a very regular approach, the Fourier analysis, and its application back and forth from the infinite series and in and out, and also its various means to get to transforms of frequency and time and in and out for Fourier analysis generally, and to then be able to frame that in higher level constructs like the orthogonal functions and their transforms. It's already been largely accomplished in the field. I mean, when Fourier invented these very techniques and promulgated them and disseminated them to the field, they were also built upon the same tools everybody else already had, and the tools of trigonometry. There are other ones, and they go on. So these are the kinds of things that, for this descriptive differential dynamics, and getting only briefly back to the non-standard part about, the exponential function and sweep, the central continuity function or sweep, that these are kinds of some things that make for an approach that then in as reasonably short a milieu as a few hours of talks or a brief manuscript, to arrive at the ability to encapsulate enough of that to make it so that any particular subfield of mathematics is much closer and it's accessible, and there's a way to traverse from it to others according to these means of categorization and this and that and so on. So it's for a model theory that's very concise, and these are the kinds of things that will keep mathematics from becoming a insensate cloistering of disparate subfields, which would be nice. So let's see then. So the discussion started from talking about these classical orthogonal polynomials, starting with Legendre in these polynomials, kind of like, and then like sine and cosine are orthogonal functions, and it's much the basis of Fourier analysis, much the basis of utility. And so the idea then was like, well, how can it be so that it can help be described what are these kinds of functions that then, as they trace over each other and make for that they would establish the envelope or the bounds of these things, that then what can be run together can be so analyzed and treated out, and then built up things like the radial basis function, or this Dirac delta, or this comb function, or something like this impulse dimension or identity dimension, ... In these organizations, catalogs, and the families, starting in the two-dimensional, one-dimensional, but in the two-dimensional, then to get to the higher dimensional of those is this, and this has just always amused me. Besides the quadratic sieve, which is that a parabola, its integer points connected by lines, intercept the axis at the composite numbers, and don't intersect the axis at the prime numbers, the quadratic sieve. Besides that, then there's the this trilateralometry, because to draw this sine function, it's usually as a matter of like Pythagoras's, right triangles to compute the value of sine and cosine and this and that. Pythagorean triples for root 3 over 2, root 2 over 2, and 1/2 or whatever it is. That's trigonometry, right? And so this trilateralometry or triangularometry is, in a sense, the idea is that sine and cosine, the functions, can also be traced out by unhinging one of the vertices of the triangle that's the equilateral triangle, not the right triangle, and unfolding it with evolving the angles at the same time as that, and then when it reaches that is laid out fully flat, to pick up the other end and roll that back up, and then to so proceed in this manner. And if you trace out the open end, it draws sine. It draws the sinusoidal function. So it's sort of a trilateralometry, right? So what I wonder is, and if you look at doing that with just like a line segment, for example, you'll notice that it draws a half circle and then another one underneath. And so it's half circle, half circle, half circle. It's a sinusoidal function of a sort. It's periodic, Does it have an orthogonal function? Yeah, you just set it off by half an angle, and it should be orthogonal in a couple different senses, maybe so. It's to be figured out. But the triangles is like so, And then if you can expand this for the square, the idea is to span this up for the square or something like that. So to figure out, besides doing the phase and this kind of stuff in the trigonometry and other orthogonal functions that are these kind of plane functions, then have volume functions, but then also to have these higher order polygons and trace those out. And to see what with regards that, wow, it's kind of remarkable. It just starts with, a periodic function that's exactly like a semicircle and another one. It's kind of like an inchworm of a sort, But it's this trilateralometry. So anyways, when I heard that was a fact, I'm like, oh, wow, kind of like the quadratic sieve, that when you draw a parabola at y equals x squared, and you connect all the integer points on the parabola and then to the other side of the parabola, then wherever it crosses the axis at an integer point, that's a composite, and wherever it doesn't is a prime. That this idea of that the sine function has a way to draw it out this way, or cosine, which is just, it's offset by 90 degrees or whatever you want to call it, or half, or a quarter rather of the period, or 2a, or a is the half period. the idea that then this can be drawn the same way, and then it has a family of other ones. That's the other thing I would want to get figured out, to figure out if then that could be making for higher dimensional analysis. Instead of taking the partials, it's like, well, we have it in 3 dimensions, so let's just take the partial 3 ways. We'll use trigonometry, because we can get a pair of orthogonal functions out of it. Well, the idea is to figure out that orthogonality isn't limited to just the perpendicular in 2 dimensions. It could be 3 dimensions, and so on. Is to figure out these higher order orthogonal functions, the integral of the product of which is 0, and then we'll work out for that, and then it can just be expressed in terms of, hey, where you can draw these in, and it's the same thing as being able to reduce the order by methods of symmetry or some other, there's some other way to describe it as well, so that then it can provide closed form solutions in that. So starting in the classical orthogonal polynomials is first is kind of paleoclassical orthogonal functions. And because you imagine that I've learned these kind of facts, but I've never really seen the derivations of them, the quadratic sieve and trilateralometry, but they exist, you know. And then the other one is these ultra modern non-standard approaches with a view of the whole field. So this is this kind of descriptive differential dynamics. Well, on it goes. Hey, have a great day.